Geopolitical disruptions and a domestic end market for electronics expected to reach $250 billion are driving India to build its own semiconductor manufacturing base. This chart shows the breakdown of a typical $10 billion fab investment. Between central and state incentives, the government is subsidizing up to 80% of construction costs, drastically shrinking the private capital required to break ground. But pouring money into construction only solves the easiest part of the equation. A fully funded building does not automatically produce a single commercially viable chip. To actually manufacture semiconductors, the physical factory needs a hyper-fragile, highly localized ecosystem surrounding it. Without that network, the building is useless. This network graph maps the life cycle of a microchip. Transforming a bare wafer into a functional device requires 3,000 operational steps. In the global supply chain, a wafer will ping-pong across international borders 20 to 30 times before completion. Creating a resilient domestic industry requires capturing and localizing that entire 3,000-step chain to insulate it from geopolitical disruptions. You cannot spread these highly specialized processes across 20 different cities. The operational physics demand a hyper-dense manufacturing cluster built from the ground up. We can see this starting to take shape at sites like Dholera. The transition from barren land to foundational infrastructure is the prerequisite for everything else. The absolute baseline requirement for any fab is a massive, uninterrupted supply of electrical power. Standard industrial power reliability is entirely inadequate here. An electricity board offering 99.9% uptime is functionally useless for a semiconductor fab. If the power drops for even a microsecond, the complex chemical processes crash. A momentary blip forces the entire factory offline for up to 6 hours to recalibrate. To achieve 99.999% uptime, fabs build triple redundancy. If the grid fails, localized UPS systems and kinetic flywheels immediately engage, keeping core machinery running without a dropped cycle. This zero variance tolerance also extends to ultra-pure water generation and sub-hour equipment repair. These strict tolerances define the ecosystem. Suppliers and utilities must be physically tethered to the fab because the manufacturing process cannot survive transmission latency. Inside the physical fab, we reach the clean room. This is where the actual physics of manufacturing take over. A new cluster will likely start by producing mature, legacy nodes. These older chips operate on low margins, meaning the factory must execute perfectly from day one. This dual line chart compares yield percentage against financial runway. While an 85% yield is excellent elsewhere, in a fab, it dives straight into extreme negative profitability, bankrupting the facility in its first year. Commercial viability strictly demands a wafer survival rate of 99.99%. Hitting that 99.99% target requires extreme chemical purity. Raw materials must be refined to 6 nines, or 99.9999% purity, before entering the cleanroom. Measuring contaminants in parts per million is completely insufficient. For process chemicals like hydrofluoric acid, tolerances are measured in parts per trillion. India has 20% of the global design workforce, but software talent cannot compensate for an operator who fails to maintain parts per trillion chemical protocols. The physical silicon must survive these tolerances. Historically, perfecting this highly localized ecosystem and training a specialized workforce requires about 25 years of empirical, trial-and-error learning. A new facility heavily subsidized by state capital cannot afford a 2.5-decade ramp-up to reach profitability. The immediate bottleneck is human capital. While the engineering talent exists on paper, there is a severe shortage of hands-on technicians with actual cleanroom experience. To bypass this physical training limitation, the industry is turning to digital twins. These are exact virtual simulations of the manufacturing reactors. A digital twin allows a trainee to adjust parameters like power and pressure, instantly seeing the consequences of their actions without risking physical silicon. This virtual environment drills strict operator protocols, like stopping immediately when a machine flashes red, long before the technician steps onto the factory floor. Without access to physical fabs for training, virtual simulation is the only method to rapidly upscale a manufacturing workforce without destroying billion-dollar production runs. During physical manufacturing, a single system inside the fab generates petabytes of telemetry data. In the past, this massive volume of data was largely unmanageable and went completely unused. This flowchart illustrates how predictive AI solves the data problem. It creates feed-forward adjustments, taking telemetry from step 1999 and instantly adjusting the machine parameters for step 2000. This computational power is also pushing the industry away from empirical trial and error and toward data-driven material synthesis. AI models are now mining decades of research papers to identify viable room-temperature chemical precursors for new materials like ruthenium. The technology slashes the number of physical experiments required to validate the next generation of materials, thus compressing the development timeline even further. If we zoom out from the cleanroom chemistry, the macroeconomic landscape of the semiconductor market dictates where a new ecosystem can actually compete. The absolute leading edge of logic chips, the 2 and 3 nanometer nodes, is controlled by a handful of deeply entrenched monopolies. Attempting to compete head-to-head at this leading edge requires unsustainable capital expenditure and overcoming decades of highly protected intellectual property. This segmentation matrix shows a more viable strategy. The entry point is asymmetric competition, specifically targeting high-volume trailing and mature nodes. For a new manufacturing hub, viability means capturing the unserved middle of the market, focusing on power electronics and industrial applications, rather than the bleeding edge. The next major technical inflection point for late entrants is advanced packaging. Techniques like heterogeneous integration offer significant performance improvements without the extreme capital requirements of shrinking a transistor node. These mature nodes and advanced packages directly serve the surging domestic demand for electric vehicles, modernized power grids, and local data centers. Constructing the factory building with state subsidies is merely step 0. True technological sovereignty requires mastering the silent, highly localized physics of parts per trillion chemistry and achieving 99.999% reliability.